Hey kids, it's me again, Charlie Busso, and we're about to start the gas class number 3. Here we go. Get a calculator. Before we do any math, though, we're going to talk about this, and this is a little on the out there side. We need to talk about the difference between real gases and ideal gases. Now, this is so important. All the gases are real. But when we talk about the theory of gases, what are gases, how do gases work, why do gases work, why do gases stay gases, we have to have a sort of a model of gases, and we call that an ideal gas. Every day when I wake up, I want to be the ideal father. I never want to yell. I want to have all the right answers. I want to teach my children to do the right thing all the time. And then I screw things up a little. I'm a real father. I'm not the ideal father. I also want to be an ideal teacher. I never want to make any mistakes, but my middle name is Mistake. There's always mistypes in the Zooms. The last one I had to pause. Instead of pausing, I stopped it. I have 2 Zooms instead of 1. I want to be ideal. I aim for ideal. Ideal is perfect. There's no perfect gases. There's real gases. And you can act ideally. I can have a good slideshow or a good Zoom, and I can have some trouble with them. I always aim for ideal. Gases tend to act like gases. That means they tend to be acting ideally. But there is no perfect gas. But we need to talk about the difference between a real gas and an ideal gas. Now, ideal gases do not exist, all right, except as an idea. Like Wonder Woman. She's not real, but she's perfect, okay? Comes to fight crime and solve problems and things like that. She has all kinds of superpowers. In the movie, she's real. In our head, she's real, but really, we know she's not. She's ideal. She's an idealized version. Second, real gases are real. They're all the gases that you know. Nitrogen, carbon dioxide, oxygen, ammonia, helium, all gases. There's real gases that are real. They're on the periodic table. And then there's ideal gases. Now, gases stay gases. They don't become liquids. They don't become solids normally because of what's called the kinetic molecular theory of gases. The kinetic molecular theory of gases explains how gases are, how gases exist, what they're doing, what the particles are doing. It explains it. But real gases, if you make them cold enough, for instance, they turn into liquids. And honestly, I mean, frozen solid carbon dioxide is called dry ice. You can buy it in stores sometimes. Right? It's not too exotic, but mostly gases remain gases. And finally, there's 2 of them more, 2 finally, D and E. Ideal gases can never become liquids no matter what, or pressure, no matter what, because they're fake. Now, if you took a real gas and you made it cold enough, it's going to become a liquid or even a solid. But an ideal gas, magic. You can squish it to have 0 volume, which is impossible, but it's magic. There'll still be a gas. You can make them absolute 0, which is impossible, but they'd still be gas, right? They're ideal, perfect, no matter what. Finally, real gases, of course, can become liquid or solids. So an ideal gas is literally like Wonder Woman compared to normal women, or Superman compared to normal men, right? Or Charlie Busso, the teacher he wants to be compared to the teacher that he really is. There's the perfect version that we aim for, or there's the real version that we are. We try to aim ideally. Some days we have good days. Sometimes we're even ideal for a little bit of time, but we're not really ideal all the time. Now, a real gas will act more ideally under 2 conditions, high temperature and low pressure. Now, what does this mean? In order to be ideal as a gas, you must be a gas. That's the most important thing. If you ever not become a gas, if you become a liquid or a solid, you fail. You're not perfect anymore. When gases are at high temperatures, the particles are moving so fast that when they do bump into each other, they break apart and bounce apart. They never collapse into a liquid, no matter what. So the hotter the gas, the less likely it is to become a liquid. Also at low pressure. If you're at low pressure, you're only going to collide into each other once in a while. There's not a lot of particles. It's going to be very hard for you to even bump into each other, and then at high temperature, probably bounce off. So if you have low pressure as well, you're much less likely to turn into a liquid. no matter what, gases have to stay gases or else they're not gases anymore and they're not ideal. So a real gas would act more ideally when it's a gas and not potentially getting close to becoming a liquid. High temperatures and low pressures keep the gas phase more strong. If you chill a gas down or if you increase the pressure and you really squash them, they're more likely to become liquids. And becoming a liquid or a solid, terrible. I just said all this. Gases at high temperature have high kinetic energy. They bang around so hard, they're less likely to stick together. And gases at low pressure have less collisions with each other. They're less likely. And the most important thing is don't become a liquid or a solid or you're not a gas. As soon as you're not a gas, you're not ideal. Good music, huh? Now, if you had 2.45 liters of neon, bigger than this balloon, but 2.45 liters of neon, you also had 2.45 liters of carbon dioxide, and you had 2.45 liters of propane, and there's the formula. And all gases, all three of these gases were at STP, the same temperature and pressure, standard temperature and standard pressure. Which of these three gases would be the most ideal, and I guess which would be the middle and which would be the least ideal? So let's look at this chart and fill it in a column at a time. The symbols for neon, carbon dioxide, and propane are this. Ne for neon, CO2 for carbon dioxide, and propane is C3H8. So for each particle of neon, it's a single atom. One atom, one particle. There's one atom in the particle. What about carbon dioxide? 3 atoms makes up a carbon dioxide. And how many particles are in propane? 3 plus 8, it's 11. So if we have 3 different gases, and they're at the same condition, same temperature and pressure, the one that's the smallest is going to be more ideal because it's going to have less intermolecular attraction. And the one that's bigger is going to be the most likely to become a liquid, the least ideal. So there's 2 ways to look at ideal gases. Under same conditions and size, and the smallest one is more ideal than the big one. The bigger they are, the less ideal they are because the more likely they'll get tangled up and turn into a liquid. Oh, if you would again, excuse me. Having too much fun. At the same temperature and pressure, the smallest particles would act more ideally. Since neon's made of single atoms, it would be the most ideal. Propane being the biggest, it would be the most likely to turn into a liquid or the least ideal. So you can compare different gases that are at the same conditions by particle size. So that's something you got to keep in your head. The smaller the particle, the more ideal it is. Here's 2 quick math problems. See if you can remember how to do this. From underneath table A, you wrote some conversion factors. You might check that now. We're going to convert 1.06 atmospheres into millimeters of mercury. You need to remember that 1 atmosphere is 760 millimeters of mercury. Oh my goodness, it's really cold in my classroom, and that's making me yawn. I want to get snuggly because I'm cold. I need a blanket, but it's really cold in here today. So here's the first math. 1.06 atmospheres over 1, and we remember the equality is 1 atmosphere is the same as 760 millimeters of mercury. The atmospheres cancel, and that comes out in 3 significant figures. Now, what if we have 844 millimeters of mercury, want to change it into kilopascals? Well, we're going to start by putting the 844 millimeters over 1, and then we remember that 760 millimeters of mercury is the same as 101.3 kPa. So the millimeters all cancel, and this is a little bit of a harder math problem. It's 844 times 101.3 equals, and then divided by 760. And it comes out this way with 3 significant figures. You should be able to do this, right? This is a quickie reminder. We just did it a couple of weeks ago. You should be good at this. We might have done it last week. All right, next math problem. 44, you have a rigid cylinder containing methane gas at 273 and the pressure is 125 kPa. You warm it up. It was 273, you heat it up to 295. The pressure is going to change. What's the new pressure? Before that, I asked you this blue question. What does a rigid cylinder imply? Why did I write rigid cylinder in this problem? What does that mean? Think, what does it mean, rigid cylinder? It means the volume is constant, right? It's a rigid cylinder. It's a metal tank. You can heat the gas, cool the gas, do whatever you want, but the gas is going to stay that size. It's not going to expand, the container is not going to expand or get smaller. The volume's constant. Now we're going to do the math two different ways. We're going to do the math with the volume canceled, and we're going to do the math with the volume included. So we'll look at this. The question at the top, when a rigid cylinder has methane gas 273 and 125 kPa is warmed up, the pressure changes. What's the new pressure? So let's see what happens. In red, starting pressure, 125 kPa, starting temperature, 273, and it's going to heat up to 295. What's the new pressure? Cross multiply, and then divide, and you get 135 kPa. Perfect. That's the answer. We're all done. What I want to show you here in black is, what if you used the whole combined gas law? Instead of canceling the volumes, what if we picked the volume and stuck it in there and kept it constant? What would happen? So in this, I kept 22.4 liters. Look, it's still 125 kPa on the top and 273 Kelvin on the bottom, but I'm making up a volume. I don't even know how big the volume is. I'm just picking a box, 22.4 liters. And on the second side, on the right side of the equal sign, it's still 295 Kelvin on the bottom. P2 is still the unknown, but I'm going to keep the 22.4 liters as the constant volume. Now, when you cross multiply, the numbers are bigger, and then you divide by a big number, and you know what happens? Same exact answer. So you could use this black formula, the combined gas law, for any gas problem. And if you happen to have a constant volume, pick a volume that's constant, or do it in red. Cancel the volume before you start, and you get the same answer. Make sure you use your units. Make sure you go slow. Make sure you cross multiply. Put the numbers in the right place. But you can either cancel the volume, or you can pick any volume. Pick 100 liters, or pick 1 liter, or 0.1 liter. Whatever you pick, just keep it the same. It's going to cancel and give you the same answer. You should probably do this. Put pause, do the math both ways. Make sure you really see this, that it doesn't make a difference. Because it's the same number on both sides, it's going to end up dividing itself away, or we can just divide the V's out before we start. Algebra is the same. Now, I love this. Avogadro's hypothesis. Remember that guy that came up with Avogadro's number? He didn't really, they named it after him. He really came up with this. And it would be a law, right? Except nobody can count to that number. You can't count that high. So it's called the hypothesis, but it always works. And this literally is so important. Like, yeah, some people have an American flag in their house, or they have a portrait of Abraham Lincoln or Martin Luther King Jr., somebody important that they think, some religious thing. This statement at the bottom is so important scientifically that you should consider hanging this up in a frame in your house, right? Maybe in a hall. Maybe even in a closet, but it's still so important that it should be hanging up in your house. This is one of those clutch sentences that really locks together science and thought and just, it's just classic brilliance. And he said, equal volumes of different gases at the same temperature and pressure have the same number of moles and the same number of particles. Doesn't matter which gases they are. If you have oxygen and helium, two different gases, but the gas samples you have are at the same temperature and pressure, and they're the same volume, different gases, same volume, same temperature, same pressure, they have the same number of moles and the same number of particles. I'm going to prove it to you, and you already, when I show you how easy it is to prove this, you'll be like, why didn't I think of that? It could have been the Arbuso hypothesis, for goodness sake. Of course, he figured this out a couple 100 years ago, but here we go. Look at this big chart. And there's Avogadro's hypothesis again, in case you want to copy it and write it down and frame it. Let's look at helium. Ready? Helium. My helium is 22.4 liters. My temperature is 273 Kelvin. My pressure is 101.3 kPa. Think about it. If you have 22.4 liters of helium at STP, you have 1 mole. And if you have 1 mole of helium, you have Avogadro's number of particles, 6.02 times 10 to the 23rd atoms. Helium comes in atoms. The other gases come in molecules, but we'll see. What if you have equal volumes of helium and carbon dioxide? Well, what if we had 22.4 liters of carbon dioxide, also at standard temperature, also at standard pressure. Well, if you have one of those big white boxes that we get painted in the room, right? What if you have 22.4 liters of carbon dioxide at STP? You have 1 mole of carbon dioxide. That's the definition of a mole of a gas. 22.4 liters of any gas at STP is 1 mole. And you would have, in 1 mole, 6.02 times 10 to the 23rd. There's a mistake at the bottom. Look at me. I try so hard to be ideal, but I can't be. Here, let me just copy that because I'll have to fix that on the next couple of slides too, I'm sure. Save from current slide. Carbon dioxide comes in molecules. Now, what about ammonia? Ammonia could be a gas, right? If we have 22.4 liters of ammonia gas at standard temperature and pressure, we got a mole of ammonia, and we have 6.02 times 10 to the 23rd molecules. Look at that. Look at that. Now the slide shows better. Now it's more ideal. We'll see if the last column's right. Who the heck knows? I try to be ideal, but I'm a real teacher. Any gas, 22.4 liters at STP, you get 1 mole. I'm going to change this one too. And you're going to have, instead of molecules, because you could have atoms or molecules, I'm going to call them particles. Because in fact, particles is a better word. It includes atoms or molecules. Look at this crazy stuff. Who is in charge? Who is in charge? I think we're probably good now. You could have gases and atoms, gases and molecules, or you could just call them particles. Equal volumes of different gases. So we have 22.4 liters of any gas, 3 or 4 different gases here, at the same temperature and pressure. And if we pick STP, it makes it easier because if we have 22.4 liters of any gas at STP, we have a mole. So we have equal volumes of different gases at the same temperature and pressure. They're going to have the same number of moles and the same number of particles. Now, if we happen to have 1 liter of each, we would have to do some mole math, but if we have one liter of helium and 1 liter of carbon dioxide and 1 liter of ammonia, I'm not really sure how many molecules or atoms we'd have, but they'd be equal. We'd have to do the math. I couldn't do it in my head, but we could do the math. We'd have to convert liters into moles and then moles into particles. We have to do a couple of steps, but equal volumes of different gases at the same temperature and pressure have the same number of moles, which really means the same number of particles. And the particles can be atoms or molecules. Fabulous. You should put that up and hang it in, maybe in your hall, in the hallway, going from like the bathroom to your bedroom. Hang it up in a hall, not in a super prominent place, but this is a classic, beautiful. This sentence is always on the Regents too. You know why? Because it's so important. And it's one sentence, and it just connects the math and the volume and the pressure and the temperature, and all gases follow the rule. And the only reason it's a hypothesis is because nobody can count the Avogadro's number. But it always works. Always, always. Fabulous. Okay. It says compare these. You do not have to do the math, but I'm going to show you the math. You can copy some of the math if you want. If you have some wacko number, 5.8 liters of helium, 5.8 liters of carbon dioxide, and 5.8 liters of ammonia, and they're all at STP, how many moles and how many particles are of each gas are present? I'm going to show you how to do this. Ready? I don't even care. Just pay attention right now. If you have 5.8 liters of helium, you have to convert that into moles. You get 0.245 moles. And if you have 0.245 moles of helium, 1 mole of helium is equal to Avogadro's number. 0.245 times that gives you this number, right? It'd be 0.245 times 6.02 equals, it equals 1.47, and the 10 to the 23rd stays. So if you have just 5.48 liters of helium, guess what? You have 1.47 times 10 to the 23rd atoms of helium. Still a lot of atoms, but it's not a whole mole. Okay, you got that many. What if you had 5.48 liters of carbon dioxide? I just put a little X. Instead of heliums, I changed it all to carbon dioxide. The math is all the same. 5.48 liters is still 0.245 moles, and 0.245 moles is still 1.47 times 10 to the 23rd they're called molecules now, they're not atoms because this is molecular. And what about what's the other one? Is there another one? Yeah, ammonia. Ammonia. I didn't even, look, it says helium underneath. I just put the blues on it. Instead of writing HE, write NH3. 5.48 liters of NH3 is 0.245 moles of NH3. That number of moles of NH3, 0.245, is going to be the same. And they're molecules because it's molecular. Equal volumes, 5.48 liters, equal volumes of 3 different gases, any gases, at the same temperature and pressure. We picked STP because it's easy. We'll have the same number of moles and the same number of particles. Moles is 0.245, and particles is 1.47 times 10 to the 23rd. Gases are freaking cool because once you figure it out, they're good for all the gases. Doesn't matter which gases. I mean, they have different masses, right? If you have that many molecules of ammonia, it has a different mass than that many molecules of carbon dioxide or that many atoms of helium. But the mathematics is all the same. How many particles, how many moles. Very cool. And we're done again. This is so easy. I'm having a great time. I'm really enjoying this. I'm a little tired. I'm a little cold. I'm yawning, but I'm very happy. You hang in there, kids, because you're learning chem, and learning chem is good, and that's all you can hope for, good, right? You're never going to be ideal. You just aim for it and be happy with good.